them together and fill up the porous space between the electrodes with electrolyte. Just by a drop on the side, it goes in by capillary forces. And then the electrical contacts, and then to drive a display the students have to figure out that you need about 1.5 volts, so you should series connect 3 or 4 cells, and then you can do that. So it's I think an interesting educational tool. You can discuss solar energy, you can discuss photosynthesis, nanotechnology, and so on. So there's a lot of things you can do with this exercise. A little bit of history of dye sensitization. This is, as far as I know, the first example of a dye sensitized system, and it has nothing to do with energy. It comes from the development of color photography. It's of course a technology which is more or less forgotten today, but to make a color photography at the time, and this is 1887, the use of a semiconductor was silver halide, and here James Moser from Vienna, he took a dye, a erythrosin dye, and put it on the silver halide, and then he could, if you can read here, obtain the visible light 1/4 of a volt. So I think this is the first example of a dye sensitized system, and moreover this paper is nice because this is the complete paper, so it's very quick to read. If you know German, you see the acknowledgement starts here, so I think it's a very comprehensive way of writing papers. We should learn something from that, I think. Then it took almost 100 years until the group of Heinz Gierischer and his PhD student Tribuch and others explained the fundamental processes in the dye sensitization. This is something of course we take for granted today. You have the dye adsorbed to the semiconductor surface, you excite the dye from the HOMO to the excited state, the LUMO, and you inject the electrons, and then you can take care of that as a current. So, but it's an interesting also path to see how you could sort of describe the basic process. Then for practical application we have to take another step, and the big breakthrough came with a Nature paper by Michael Gretzel here and Brian O'Regan, 1991, where it was really an order of magnitude increase in efficiency, from something on less than 1% up to 7% efficiency. And it was really also a change of the way of looking at how can you do efficient solar cells. So this was the big secret here, is that you can use a mesoporous high surface area electrode, and that according to textbook should in principle at the time 1991 not be possible. You should have very pure semiconductors, p-n junction of silicon cells, avoid defects. You built in an electric potential, so when you excite the electron hole pair they are separated in the electric field. Electron goes to one way and the holes in the other way, and so you need that electric field to separate charge. You need defect-free and avoid surfaces, because the surface is a defect in itself, let's say. And here comes a system then which is based on surfaces. It's a lot of huge surface area, 1,000 times larger surface area than the projected, let's say, based on porous system. The first question I remember as a PhD student we worked with back at the time was, where is this electric field to separate the charge, because we have nanoparticles and they are too small to have an electric field inside one particle. So where is this electric field? That was the big question, and we were struggling with that question for a year almost, and then someday we said, okay, let's forget about the electric field. Are there other processes which can make things to be transported? And the simple idea we came up with back in 92, 93 was to say, well, for some reason of kinetic origin, the electron, when it's excited of the dye here, it's injected and it moves through all these particles to the contact without big loss. It's almost 100% and short circuit of electrons going through here. So we don't lose them on the way, let's say. And the only place where we can take out the electron is at the contact here, and then we have the outer circuit. So that means that we have lower concentration of electrons at the contact, higher at the outer of the film. And for a chemist, a concentration gradient is diffusion. So we presented a diffusion model to explain the transport, and that became first a lot of skepticism, I would say. People wanted to see this electric field, but nowadays it's very established, and the transport is more discussed now in more of the details, let's say. So another reflection on this picture is that it's interesting to see how challenging it has been to change the material components. We started in the early 90s with TiO2, nanoparticles, ruthenium complexes as dyes, iodide, triiodide as electrolyte, and I would say to really have some contender new dyes which can be better than the famous ruthenium complex took maybe 15 years to find, let's say. Almost the very first one was the best. To replace the electrolyte took us 20 years almost of research, and I will tell you the story behind that. Still, the mesoporous TiO2 is still the best material as a substrate. So it's very, very difficult to change and one component. And I think the reason is that it's a complex system, highly interacting, so you cannot change one parameter. When you do that, you change a lot of other properties, let's say. So you really have to think about the system in the device. So here was the explanation also for the charge separation. I said you had a built-in electric field for charge separation. We could explain then after some years that actually the die architecture can separate the charge itself. So this is the famous N719 die from Grethel's group. It has these thiocyanide ligands and the carboxylated anchoring groups. And when we studied with synchrotron and quantum chemistry, where we have the excited electron, we found it to be on the pi star orbital of carboxylic groups. And that's very favorable because that anchors to the TiO2, so we have a fast injection. The hole, on the other hand, is much located on the sulfur. So by this principle we can understand that when you excite the electron goes to the TiO2 and the hole goes to the electrolyte side. So we can really separate the electron hole by the die design itself. And the kinetics is then very favorable. You inject very, very fast, femtosecond time scale for the best dies, let's say. Regeneration is the key for further improvement, I would say. Typically microseconds, and then we have the loss reaction. The electron can react back to the oxidized dye. Depends a lot on light intensity, but typically millisecond. Or, which is often the case, the electron is lost to the electrolyte, and that's also a millisecond time scale, let's say. And this the two processes we have been working with the last years to improve efficiency is on looking into the regeneration process, and also how we can avoid this loss reaction from electrons to the electrolyte. Short on industrial scale of the technology, we have, I would say, for indoor application, let's say low light application, I would say the technology is very ready for commercialization. It's stable, high efficiency, and so on. If there is a market for indoor, well, that's to be seen, I would say. If we do a little bit more advanced application like building integration, here is an example of a company making this facade, about 100 square meters, was exposed in the World Expo in Milan last summer. And there are a few of these kind of facade demonstrators in which one can see. If we would like to see the die cell competing with silicon and large-scale electricity, I would say no, we are not there, we are not competing. We need one or two more breakthroughs, both in terms of efficiency and stability. And as an academic group, it's here where we can perhaps do some new contributions. So I will focus a little bit now on where I think we can see improvement in efficiency. And to do that, we need to do some analysis of the conventional system. So this is a simple energy level diagram of the conventional system. Let's say it can be this ruthenium complex. Here is the TiO2 conduction band. You excite, inject, and then you regenerate with iodide, triiodide, and if we draw the energy levels here, we have a redox potential of iodide, triiodide, the oxidation potential of the dye, and here is the big loss in this system. The internal potential drop here is about 0.6, 0.7 volts. The open circuit voltage we get is from the Fermi level of TiO2 and the redox potential of the redox system. So typically 0.7, 0.75 for iodide. But here is the problem, let's say. And the question we asked in Uppsala a few years, how much potential drop do we really need to regenerate the dye efficiently? So that's we call the driving force. The driving force is this delta G difference between the redox potential and the dye here. Do we really need 0.7 volts, let's say? And we made the analysis. So iodide, triiodide is not a simple redox system. It's a 2-electron process. It goes through intermediates. And the intermediate of importance we identified here is this iodine radical. So really the driving force to regenerate the dye is from this redox system, iodide, iodine radical. And the difference here was not easy to measure, but we think it's around 0.3, 0.4 volts. The rest of this 0.7 is just to let iodine radical react with an iodide to form the I3 minus. So this is the problem with the iodide system. We lose potential there, and the benefit on the other hand with iodide, triiodide is that this reaction of electrons here with electrolyte is very slow. So as soon as you change your redox system to something else, you really open up this process to be much faster. So if you take ferrocyanide and classical redox system, the problem is really that the electron reacts quickly with the electrolyte. So to solve that problem, you need to passivate the surface somehow. And it's been a lot of tries to have insulating alumina oxide, zirconium oxide and so on the surface, but not very successful. But our conclusion here in 2009 was that if you really want to have a new breakthrough in efficiency, we do have to change the electrolyte and to passivate the surface. So we started up that as a PhD program, but we knew it was very challenging. But we had a piece of luck, I must admit. This was not really planned, as often in science the big discoveries are not really planned. We made this dye. It's an organic dye with a collaboration with Lee Cheng-sun at KTH Stockholm. It's a triaryl amine unit. This is the donor group. This is the linker, as we call it, and this is the anchoring group. Now the problem with these organic dyes are normally that they aggregate on the surface. So the design here we did to avoid aggregation was to bring in these alkoxy groups. So the idea was really to break aggregation with these alkoxy groups, that they point in different directions. That we could observe was the case, so we were happy about that, but we had a bonus effect. What happened with this dye was that it passivated this recombination reaction. So this reaction of electrons to the electrolyte was 100 times slower with this dye than we had ever seen before. So that means that the dye itself can passivate the surface. And then we were thinking, now maybe we have a chance to change the redox system. And our first choice came from work on nickel oxide as a P-type photocathode dye sensitized system. And it was to use this cobalt trisbipyridinium complex as our new electrolyte. So it was really a combination of things. We had dye development with Stockholm. We had Sandra Feld who worked to try to find alternative redox system. Libby Gibson worked with P-type photocathodes, and when the three of these met and so on, we could present this 2010, and I remember I presented the result in a conference in Korea. It created a lot of interest because this was the first time that we had something else than iodide, triiodide, which worked. So Gretzel, he called me 2-3 weeks later. He said, Anders, you are right, cobalt works. We have 9% efficiency. We published, and then he called a few weeks later. We have 11% efficiency. So I thought, okay, we leave the high efficiency to EPFL, and then they published at EPFL the best is 13% efficiency. But the published best value now is a year old. It comes from Japan. It's a company called Adeka. They use the cobalt complex, cobalt phenanthroline. They publish 14.3%. I would say this seems to be very hard to reproduce. It's also interesting, it's a co-sensitized system, we call it. This is their own organic dye, and this is the dye we developed in Uppsala they use. And these two together give this high efficiency. So with the cobalt complex, I would say 13-14% are the published record. With iodide, we have a certified efficiency record of 11.9. Question now, can we take this further? And let's see. The next analysis to do was what is now the driving force we need for cobalt complexes. We had 0.7 volts needed for iodide. Can we do it lower with the cobalt? And you see here the sketch. This is now the difference in driving force with the redox potential, because you can tune the redox potential of cobalt with the ligands here. So you can really have a nice window of redox potentials, decreasing the driving force. When you do that, you also slow down the regeneration, so there must be some optimum. Of course, when you go more and more positive, you should also increase the voltage, but there is an optimum. And to make a long story short, we found that for cobalt we need 0.4 volt in driving force to efficiently regenerate. If we are lower than that, with higher redox potential, the regeneration becomes too slow, and we have problems with recombination because of that. So what we dream about is to find a redox system where we can regenerate, let's say with 0.2 volts or something. That would be your dream target. And we maybe have one system which we are excited about now, and that's this copper phenanthroline was the starting point. It was published by Peng Wang in China first at 7% efficiency. We took that up, and what you see here is that the redox potential is very positive. The driving force now is less than 0.2 volt. Still it regenerates very efficiently, and the efficiencies in the first attempt we did was very similar between copper and cobalt as electrolyte. But the nice thing here with copper is that we have higher voltage, 1 volt here compared to 0.88 for cobalt. So we do have a redox system which regenerates very efficiently, but with the low driving force, and we can get the voltage out. So this is really what we are working on very much at the moment. We have the best results now is about 11% efficiency with these copper complexes. Another bonus effect, which also was very unexpected with the copper, was that when you work with dye-sensitized cell, it's normally a liquid electrolyte, and the problem is then to seal them, because the liquid, the solvent evaporates and it leaks, and it's all kind of practical problems. And when a solar cell has leaked electrolyte, it's normally dead, doesn't work. I don't know really why, but we had these dried out copper liquid systems, and the technician in Uppsala, I think he had nothing to do really, so one Friday afternoon or something he took this dried out cell and measured them, and strangely it had higher efficiency than the liquid cells. So we are not really sure what this is, but it seems like a kind of solid state copper complex system. Dried out cells work as well as the liquid system. So for this we call them solid state, although there may be some solvent molecules left and so on, but it's definitely a different type of electrolyte than the normal liquid one. We also for these cells have about 11% efficiency at the moment. We call them the zombie cells because they should be dead, but they are alive. So we got the cover on the EES here, and we had an artist from Iceland. She drew these zombies here coming to change the copper complex on this one. So it's a very interesting system. This is a conductivity test in the liquid state. That's the red ones. That the resistance is higher, and you see the conductivity increases when we go to the zombie stage when it's dried out. So it's some change of also transport mechanism. This is unpublished, but we also measured for indoor application. Of course, as a Swede, we take a light source from IKEA, 200 lux, so this is like we have in here. And the comparison is interesting. We have our copper dye-sensitized cell giving at this 200 lux about 15 microwatt per square centimeter, And it's actually, this is the champion, I should say, but it's actually higher than gallium arsenide solar cells, and that I think is quite interesting. So gallium arsenide is of course the very, very best solar cell with 29% in sunlight, let's say. But in indoor here, because we can match the lamp spectrum and so on, dye sensitized cells are really competitive. So maybe it's at least as good as gallium arsenide for indoor applications. Then I switch over, that's where we are with dye cells, that's our direction. We have hopes with the copper complexes. It's of course difficulties too, and then a lot of work needs to be done on the counter electrode and so on, but there is this favorable, interesting point with the low driving force. Also, the platform of dye sensitized cell has been a very interesting development over the years, because you can of course replace and modify the components. You can replace the dye with quantum dot inorganic semiconductors as light absorbers. As I said, you can replace the liquid electrolyte with a polymer or a solid state hole conductor. You can even think about doing solar fuel, so you bring in, this is nickel oxide with the dye, and the dye now reduces cobalt catalyst, and we could see some hydrogen formation in this device, and you can do tandem structures and so on. So there's a lot of chemistry you can do, let's say. If you now take an inorganic semiconductor like a perovskite structure, and combine then with the classical solid state hole transporter, which is called Spiro, then you have the beginning of what we call perovskite solar cells. And the starting point is from Tom Miyazaki. It's an old friend, and he is a keen violin player and he's a hobby of violins, let's say. Another hobby he started early 2000 was to try to use perovskite material as a light absorber in a quantum dot solar cell. He started, as far as I know, to talk about it 2006. He said that I have this perovskite, I have 2-3% efficiency, but I have to be very fast to measure it with the iodide electrolyte, because it's stable for maximum 10 minutes. So I really run into the solar simulator, do the test, and then it corrodes. So that was, and he published this 2009, and then the breakthrough really came 2012, and what it was based on was that you replace the liquid iodide electrolyte with this Spiro solid state. Then you avoided corrosion, and also the efficiency went up. So the breakthrough papers came from two independent work. It was Namgyu Park in Korea who did this together with Michael Gretzel, and then Henry Snaith at Oxford took contact with Tom, and they published also very much the same result, about 10% efficiency, perovskite and Spiro, and so on. There was something in the very early on from Henry's paper which said that this is maybe something else than just replacing the dye, and that was the experiment they did as a blank first, and that was to check how fast does the electron recombine in the perovskite layer. So they used alumina oxide as an insulating oxide. And very strangely, they saw that the efficiency with alumina oxide was even higher at the time than TiO2. So that means that you don't need an injection like in the dye cell from the light absorber into TiO2. The perovskite can really conduct electron on its own like this. So that shows that perovskite is another kind of material. And another interesting paper in the early days here of perovskite was from Leo Setkar in Israel now, and he could see that he can do perovskite on TiO2 without the hole conductor, just deposit gold, and then the perovskite also conducts holes very efficiently. So that was a kind of opening to say this is something different than others. Perovskite is organic, inorganic. This is the classical one. It's a methylammonium cation. It's lead, and it's an halide like triiodide. This is the perovskite structure. You have the cation in the middle here, the lead here, and then you have an octaeder of the halides like this. So that's the perovskite crystal structure. It has a good band gap, which you can tune by substituting the halide and the cation. So this classical one is about 1.5 electron volt. So the starting point was to use this perovskite, and then you had TiO2 and then Spiro as the hole conductor. So very much like a dye cell, you inject electrons into TiO2 and holes into the Spiro. It has low exciton binding energy, so you really separate the electron hole pair very quickly and efficiently. So it's a very ideal semiconductor, and you can prepare it from solution. That's the real interesting part if you compare to silicon and gallium arsenide. So it comes also and developed in different kind of geometries. This is the sort of starting point resembling the dye cell with a mesoporous TiO2 layer. You have the FTO glass, compact TiO2, and a very thin layer of mesoporous. We are using now 100-200 nanometer TiO2 pores. Then you impregnate with the perovskite, and then the hole conductor and gold. You can also do it much even simpler to remove completely the TiO2 and just use a thin compact layer of perovskite hole conductor. This is what we call the planar device, and if you come from OPV, polymer solar cell, you tend to start with the whole transporting layer instead. This can be nickel oxide, perovskite, and then an electron collector on the top like this. We call that the inverted structure. And it's a lot of applications coming up: LEDs, tandem solar cells, photodetectors, lasing, and so on. So it's an interesting material in itself. So now I will say something about what we do at EPFL. We started, before I arrived at EPFL, they started to mix the perovskite. So here is 15% bromide, for example. It tunes the band gap a little bit to larger band gap, but it also stabilizes the system. And you can also tune the different cations. So this is a mix of formamidinium and methylammonium. It also forms higher quality perovskite films, let's say. So this was the starting point to use mixed system. And that we have published early this year at about 21%. What you can see from the SEM picture here is really that it's a very thin layer of mesoporous TiO2, 1-200 nanometers. Most of the perovskite is a compact layer on top. We call it the capping layer, and then the whole transporting medium and gold as a contact. So here we optimized the mixed ratio. We saw that excess of lead iodide was beneficial, passivating recombination, and besides having a nice efficiency, we also measured a very high and nice electroluminescence, about 0.5% at the solar cell voltage. And this is very high. It is as good as the best silicon solar cell. A dye-sensitized cell is about 10 to the minus 6 in comparison. So this is a very high electroluminescence, and I will come back to that. We continue the optimization, and this is a recent work where Dongxin Bid postdoc worked on additives into the formation of the perovskite with PMMA. It forms a complex with lead iodide. It slows down the crystallization. We form larger crystals. So a big game for perovskite is to form larger crystal and to reduce grain boundaries, let's say. And if you do that, you get higher voltage and less recombination. So with this was certified at 21.0% efficiency. What you see also here is what I said with the PMMA additive. We can see that we form an adduct, a complex with lead iodide. It retards the growth, improve crystallinity. So this is without PMMA. Smaller crystals, we enlarge them with some PMMA. This is the optimal concentration of the PMMA. Larger crystal, less grain boundaries. Higher concentration, we seem to have a precipitation of the PMMA. It doesn't work anymore. So the result here, we had 21.0%. It was certified a year ago, and we were very happy because it was the world record. At the Christmas party, Gretzel was running around with this certified record. Then in March this year, Professor Suk from Korea took the world record back to 22.1%. That's the world record at the moment. For small cells, I would say this is 0.15 square centimeter. Of course, what you can do in this world record hunt is to change the game a bit. And another world record, which is done is to have at least 1 square centimeter area. Then you come up in the world record tables published in Progress in Photovoltaic. So we worked on 1 square centimeter cells. And what we did there is when you spin coat the perovskite solution, perovskite starts to form, and then what people normally do is to add what we call an anti-solvent. You reach supersaturation of the perovskite and you form a higher quality film, shiny, smooth and so on. We replace this anti-solvent with a short and quick vacuum flash instead, so we can do larger areas. And that was published in Science early this year. And we could then obtain a new world record of 19.6% for 1 square centimeter cell. Then we were happy again, of course, but only for a week, because then Professor Zook had 19.7%, so that's where it is today. So, but anyway, it shows also that you can have larger cells. We have continued the path about mixing, and it's an interesting concept. So Michael Saliba, postdoc here at EPFL, saw that some work started with inorganic cations also, like cesium, having a bit better stability, and he added then cesium to our mixture. So this is now 3 cations: cesium, formamidinium, methylammonium, in the mixture iodide bromide. Nice IV curves, 21% efficiency, but what is interesting here to see is if we do without the cesium, we do have some impurities in the perovskite film. This is XRD, this is the perovskite peak, this is lead iodide, and this is a yellow delta phase which is not photoactive. So these are 2 impurities coming without the cesium, and with the cesium we really decrease these 2 impurities. So we form even larger, higher quality crystals with this mixed system. And at higher concentration of cesium it's the same. So this is our standard protocol, I would say, at the moment. We can see here that without the cesium, well, it's not bad, it's good, the crystals, but with the cesium 5%, really columnar structures all the way through the compact layer. So again, larger crystals, higher quality films, and that also increases the efficiency and, more importantly, stability. So this is a stability test over 250 hours. It's full sunlight and operating all the time, so it's maximum power point, we call it. We start at 20%, you see then it's quite stable for 250 hours with cesium. Without, we have a much faster degradation, let's say. So it improves stability. This is now still room temperature, so I would come back to this question, because what happens at high temperature, that's the next thing. But cesium improves the stability, let's say. Well, why not? So Michael Saliba, he said, okay, let's try to add more things. So this is our latest results. It's now 4 cations. So now we add rubidium, so it's a quadruple cation, published a month, 2 months ago now maybe. Also very nice crystals formed, and you can ask, why is this good with this mixing? Here is one result. Again, we have this phenomena that we reduce impurities with this mixed cesium rubidium. But you also see here, this is if we have the MAFA compared to the quadruple here, this is the fluorescence. You see it's before annealing. So we have here formation of not complete perovskites. There is some emission which is broad. We have some impurities from the XRD. If we have this mixing, we have a nice sharp fluorescence peak, and we have removed some of the impurities. If we anneal at 100 degrees, you see the fluorescence peak overlap completely. So with the mixing, we do form perovskite structure at room temperature, we think, at higher quality. So that's what we think is happening with the perovskite formation. So these are the results. With the rubidium add almost 22% now. It is working as an LED. This is a solar cell which we just switch, so we inject current instead. It starts working as a light source. So red LED, there is a solar cell which is not an LED behind here, so 2 solar cell works nicely. So with this we have highest efficiency, 21.6, This is very interesting, I'll come back to that. It's a very high voltage, 1.24 millivolt at maximum. The band gap is 1.63, and it's the theoretical highest voltage we can have is about 1.33 volt. You always have to get rid of about 0.3 electron volt from the solar spectrum because of entropic losses in the sunlight. So the highest theoretical VOC we can get is 1.33. We're only 90-100 millivolts away from that. It means that it's a very, very high quality semiconductor. So it's among the lowest loss-in potentials for any kind of PV material. I think it's just gallium arsenide which is better. And we have now an even higher 4% electroluminescence yield at best, 1% if we have solar cell conditions. So I'm coming to the end. What about stability at high temperature? That's the last question. We had some insight also published this year that a problem at high temperature, because we use Spiro and we use gold as contact, and we tested them at 85 degrees Celsius and they were completely degrading very quickly. So it's no stability with that, and we thought it had to do with the perovskite film is unstable. But so we did a sim study and to see what elements do we have in the structure. Surprising to us at least was that we had a lot of, or not a lot, but we had gold in the perovskite structure. So gold diffuses through the Spiro into the perovskite, and that's the cause of degradation. It had nothing to do, we think, not much at least, with the perovskite. It is the gold Spiro contact at high temperature which is the problem. So that was very important for us, because then we could start to think what can we do about it. One thing we did was to bring a very thin layer of chromium between gold and Spiro, and then you see this improved the stability. This is with chromium, without. You can also say, okay, let's not use Spiro anymore, use a polymer as a whole conductor, which maybe is a barrier to gold diffusion. So that's what we did in this work here, and this is our latest stability data. So it's 85 degrees now, it's 500 hours, full sunlight and operating all the time. So it is as tough as we can do it according to protocol. And you see the stability is very nice here. So, and this is now using a polymer instead of Spiro. That is the trick to get the stability. So I think now at least we can say that the perovskite solar cell is not unstable, because that people have said for a long time. They can be stable, we think. Of course, more work needs to be done here, but this is encouraging. We collaborated also with a group from Torino, Federico Bella and Italy, because in, let's say in this work, we are not good to seal cells at BPFL, so this is under nitrogen atmosphere, so it's no sealing here. So what they did was to do sealing, and they sealed it with a PMMA polymer. They did two things: they sealed the cells, and on the top of the top layer in the PMMA they brought in some fluorescent dye molecules which convert UV light into visible light, because two problems here is UV light and of course humidity, water dissolves. So they solved two problems in this work. One was to solve the UV problem and even increase the current a little bit in the visible part here, and the other one was to avoid humidity. So the stability data here now is with UV exposure. The blue line is with these fluorescent molecules on top, very stable for 175 hours under continuous UV light. And you see, if you don't have, if it's no sealing, it goes very quickly down. If it's sealed but without the fluorescent molecules, it goes down. And they did also outdoor testing in Torino, so this is now for half a year, I think they have been outside, and looks very stable, let's say. So I'm coming to the end, and that is to see how far can we go. There is a mechanism for gallium arsenide, the best solar cells I said, and they lose very little VOC. Here is the theoretical Shockley-Quasar equation. The VOC you get is the theoretical minus the external luminescence. So a good solar cell with good VOC should also be a good LED. So the recombination should be radiative, then it's an efficient solar cell. If you go to VOC and you have luminescence radiative recombination, that's a good quality. So VOC goes together with the electroluminescence. And gallium arsenide has high values here. And the reason is that it's something called photon recycling. What you can do in photon recycling is that you excite something in the layer of gallium arsenide or perovskite also. Then that can emit, if it has a high radiative recombination, it emit the photon and it can be reabsorbed within the layer and emit and reabsorbed and so on. It's called photon recycling, and it was shown by Richard Friend and his co-workers this year that perovskite has this photon recycling mechanism as the gallium arsenide have. Silicon does not have this. So this means that we can compare this electroluminescence should be high. So for gallium arsenide we have the best is from Alta Devices, 22%, and also from Germany 1.3%. That's the very, very best. You see silicon, the best cells, has an electroluminescence of 0.6%. If we go to CIGS, cadmium telluride, it's 0.2 or 0.06. And if we now bring in our values for the perovskite at 1%, you see that we are actually better than silicon, and just gallium arsenide is better. So we have to see how far this can take us, but from a fundamental point of view, the perovskite shows very, very interesting fundamental properties. So with that I finish. I summarize the dye cells. We think copper complexes are interesting. I should say that the practical applications on dye cells are using iodide, triiodide. That's where we have the most stable devices. Stability with copper and cobalt is to be tested, let's say. And for perovskite cells, yeah, we start to see encouraging stability data and efficiencies, as you see, very interesting. So with that, I just thank my team here in EPFL, and of course we work very, very closely to Grätzel, so we are in the same corridors and labs and so on. And with that, thank you for your attention as well.
The speaker is now open for questions.
Are you still making dyes in your lab?
Yeah, we do some, but it's less than before, let's say. So I would say that most of the new dyes we are using comes from the work we did in Sweden. That's these triarylamine dyes. There is also some dyes which we use coming from China and so on, and so it's more activities on the copper complexes itself at the moment, and then trying to combine with existing dyes at the moment. But it is interesting for us to collaborate with people doing dyes. Let's say that we are always open and interested to do that. So it's not the, I think the peak of synthesizing dyes at EPFL was with the ruthenium complexes and so on.
One question regarding your Swedish dye with ortho-alkoxy group. What can be placed in an ortho position before the rings start bending too much, so you have no benefit of that?
Yeah, that's a good question. But what we have done in terms of experiment is to vary the length of the alkoxy chain, and it doesn't seem to be making so much difference if we go from methoxy to butoxy or hexyl. The 4 or 6 carbons seems to be the better one than just a little bit smaller one. But that's a good discussion. I have no good answer to it, let's say. But what we have done is that series of tests, let's say, that exists.
Okay.
Thank you very much. An extremely impressive talk. So the open circuit voltage losses of the perovskite is what I think everyone is always amazed by. But the one thing I never understand is when you see the papers, there's maybe a 0.4 electron volts variation depending on who's making it, what's making it. What's sort of the origin, like in any other solar cells? the same material gives the same open circuit voltage, but it seems...
Yeah, no, it is a good question. I think it is improving on reproducibility, I would say. I can only more or less say from our experience at EPFL how it goes. The high voltage of 1.24 volt we measure without a mask, so because there is one technical problem here when you do solar cell testing, and that is that you use a mask, and that mask area is open area is a little bit smaller always than the solar cell area, so you have a dark area, and that's where you have some losses actually. So the VOC decreases there. So you really want to have as small dark area as possible. So, and we have still, so when we measure and certify we have 1.15 volts. When we take away the mask we get 1.24. So now just to improve efficiency it's how to minimize it, and it has nothing to do with just, so we are working on the mask at the moment, things that can do that. More seriously, we feel that with the triple and also with the quadruple, it's a little bit more complex. We do get higher reproducibility. It was quite interesting when we submitted the triple cation. We claimed that we had higher reproducibility in statistics, and then one of the referees said, "Okay, show us. Is it only one who can do it in the lab, or can more people do it in the lab?" So we had a project we had 3 people in the lab separate doing, and they all 3 came to higher than 20%. So we do have a handful of people who are 20%. Then things happen. We had last month problems with our evaporator of the gold, and for a month we had low efficiency and problems. So just to let you, it's not perfect in any lab. I think it is hard work behind it, but I do see also some positive trends in reproducibility. Then I know know from Singapore, I mean humidity is a problem. So Singapore I know are fighting still with efficiencies, and we think it has to do with humidity problems, and they buy a new glove box, and you know, it's all these kind of things going on.
Thank you for the presentation. Going to the humidity issue, so in terms of accelerated lifetime, if you do humidity test, this is the problem there. So I saw the progress in temperature and great data, but what about humidity?
Yeah. No, I think it has all to do with the sealing. So you have to have a very good sealing. So in this work from Torino, I should say, with their sealing technology, they also put I didn't say that, but they took our cells with the sealant and brought it into desiccators with boiling water in the desiccator. So it's really 100% humidity in there. And for a week they tested, and it was the same efficiency. So if you, but its sealing is the key thing.
And second question about the planar devices.
Yeah.
You said you're going to comment on this, but from my side, I will say that it's better for production, so it's more easy to print.
Yeah, so because I was worried about time, but so I can comment on it. What we do there, well, the trick for us was to change from, you have the FTO glass, and then for fundamental reason we were interested in the contact material, so we tested different oxides. And we were surprised because for us the best was tin oxide. So we do, first we did an ALD tin oxide, so what you want is the most compact and thinnest possible. So ALD tin oxide, the perovskite, spin coated Spiro, and the gold contact. And then we published 18-19% last year. Then we felt that it would be interesting to see how far we can go just by spray pyrolysis or chemical bath of the tin oxide to avoid the ALD. And that's tricky, and I would say reproducibility is an issue, but if it works, we have published now 20.8% efficiency on planar. And to me that is and the highest temperature in the process, as you say, is 150 degrees Celsius. So it's very, very interesting for me. If a company asks what would you do for sort of production, I would go for the planar actually. And So in the lab we have 22% compared to the I talk champion cells now, 22 compared to 20.8. It could, I'm not sure it's really significant. We have 1 or 2 people working on planar, and with Gretzen's team and so on, I don't know, it's 15 people working on the TiO2 side. So just statistically it can be just similar. I see no fundamental reason why planar should be less efficient.
Thank you.
Thanks for a very nice talk. I'm just wondering if there's been any attempts to replace the lead in the perovskites, and if so, what are the results from that?
Yeah, no, it has the hope has been a bit disappointing. It is people have tried a lot of things. From the most obvious one is tin. And I think the highest efficiency on tin on itself is 6-7%, and there are hysteresis problems. People say also that tin is not so much better than lead actually in terms of toxicity and so on. So it's, but that's the best so far. There is, and people have tried all kind of things. The other one which I think can be interesting is bismuth, where at least people see nice perovskite structure formed, and there's also a group at Stanford doing bismuth silver as a combination. So you take the classical, if you have to replace the 2+ lead, you take 1 3+, 1+, and then see if you can combine. So there is, but still not so high efficiencies there, but that's interesting. It's important work to do, but so far very, very, very challenging, I would say. There is interesting work on lead tin mixtures, which because you tune the band gap to the lower side. So with the halide you can go to, if you have only bromide you have a band gap of 2.2, and if you go to chloride you get higher. So you can and then the cations can also be part of the tuning. So you can really tune from 1.56 to 2.67 and very, very nicely. The more difficult is to go to the lower band gap, and that's why tin becomes interesting. So with just tin you can go down to 1.1 like silicon. So with the mixtures there you have possibilities to tune. So that's why that is interesting, and it comes in when you make tandem cells. You want to have the ideal band gaps for the top and bottom. So that's where it is, but that's so far very, very challenging.
Yeah, in the interest of time, let's thank the speaker again.
Thank you.